Hi, this talk is all about geolocation, augmented reality, and Pokemon Go. In the early days of desktop computing, humans could only interact using a keyboard. The first desktop computer was launched by the Italian company Olivetti in 1964. This was really a programmable calculator and there was no screen, just a narrow roll of printer paper. In 1973, the Xerox Alto desktop computer was introduced, with a screen and even a mouse. 11 years ahead of the Apple Macintosh. The options for interaction are now vastly extended, with powerful networked computers with high-resolution screens and cameras as part of almost every mobile device. A form of advanced visual interaction, known as augmented reality or AR, has had a fairly slow takeoff. The term dates back to 1990, and the first AR apps appeared on the iPhone in 2009. By mixing computer images with live-streamed video, AR initiated the leaking of the digital world into the physical world. Another way in which computers have leaked into the real world is through the Internet of Things, or IoT, in which everyday objects and devices are connected to the internet. The devices become smart and can communicate with remote applications on the cloud or on your phone, for example. The earliest IoT example is a 1982 Coke machine. The machine was modified at Carnegie Mellon University to report whether it was out of drinks. Augmented reality is a way of blending together visual images from the physical and real world. This blending happens in real time, in a 3D space, interactively as a user moves around. With mobile devices, AR makes use of the device screen and camera, turning the screen into an optical see-through display, or known as OST. The screen shows the camera view, but with the computer graphics superimposed and aligned according to what the camera sees, or the phone's location sensors, or geolocation data, or any combination. Geolocation coordinates identify where a user is in the world. This is possible because mobile devices can access the Global Positioning System, or GPS. GPS uses a worldwide radio navigation system incorporating 24 satellites and their ground stations. Geolocation coordinates are accurate to better than 3.5 meters horizontally. You can access the geolocation coordinate data and send it to Google Maps via Google's API to return the user's location on a visual map. All of this is straightforward in HTML and JavaScript, and it runs smoothly on a mobile device. So let's have a look at some of the categories of AR, and we'll begin by talking about sensor-based AR. The advantage of sensor-based AR is that it doesn't require image recognition. The device can superimpose digital images onto a camera view based on geolocation and location sensors. The geolocation data is supplemented with orientation data from the device sensors to work out which direction the user is pointing their camera in. This approach could be used, for example, to superimpose information about a landmark building when a user is close to it. Sensor-based AR can cause problems with time lag as the location data has to update. The GPS precision of about 3.5 meters is not enough for most augmented reality applications. Also, geolocation generally won't work indoors and it can be blocked by tall buildings. An example of sensor-based AR is shown in this image. Ingress is a massively multiplayer online role-playing game that was launched in 2012 by Niantic Labs, originally a Google startup, and now Niantic Inc. Ingress developed a cult following, but it has never really achieved mass popularity. And you can see from the image what's going on. When you're in the location of a landmark, this information is getting superimposed on the image, and you're getting clues as to this large multiplayer game that takes place in real locations. So although Ingress was not a big hit in terms of mass popularity, the breakthrough moment for Niantic came when they launched Pokemon Go in partnership with Nintendo and the Pokemon Company in July 2016. Based on the same technology as Ingress, Pokemon Go became a global phenomenon as the world's most downloaded app ever, with 100 million downloads in the first month and 500 million in 2 months. The task is to capture AR Pokemon that are shown in real locations on a map and do battle in location-based gyms. Although the game is free, 20% of players are making in-app purchases. In-app payments in the first 5 weeks when the game was available in 3 countries were $268 million, with 13% of the adult population downloading the app and 90% still playing the game 4 weeks later. And you can see this crazy situation where people were playing it all over the world, wandering around parks and cities. But there's an interesting element to the Pokemon Go app, which is to do with location-based advertising. We're just going to have a look at how that actually works. So if you've played it, you might recognize this screen. What we're looking at here is in-app lures for sale in Pokemon Go. A very new form of in-app purchasing uses sponsored locations. This was more or less invented by the Pokemon Go game at launch in July 2016. I have discussed Pokemon Go in terms of augmented reality, but think about it in terms of monetization as well. Brilliant move, selling sponsored locations called Pokestops to the likes of McDonald's, pubs and movie theatres. These sponsored locations feature attractions for the user. People congregate at the sponsored locations and spend money at the businesses there. Business buy the in-game lure item at a cost of about 100 Pokecoins or $1 to attract users. The lure lasts for 30 minutes but can be repeated. So the success of Pokemon Go was a big surprise, but Niantic is now figuring out other ways of leveraging these kinds of sponsored locations, which could include pay per visitor, for example. In-app advertising in games is unwelcome by consumers, so this new model is of great interest to businesses that can effectively piggyback off the game without disrupting the game experience. Some brands may choose to do this in preference to creating their own gaming app that is built around their brand. It's very early days for sponsored locations, but the model has definitely arrived. If you can persuade businesses to make in-app purchases to help direct users to their locations, then you have got this model to work. You don't need the weight of Pokemon behind your app, but you will need something compelling. Your app will need to use GPS and maps, although it doesn't have to use AR. You could design anything where map is needed. It could be a dating app, for example. Let's have a look at how Pokemon Go actually works. How does this location-based AR actually work? To do this, I'm going to do some drawing. So first off, let's imagine a location with a landmark, and I'm going to draw an elevation of this. So here's the ground, and maybe it's like a statue in a park or something, so it's got a little plinth. There we go. And I'm going to put the statue on here. Like so. And we're going to draw, that's the elevation, we're going to draw the same thing in plan. So you get the guy, the statue's head. Here's the plinth. Okay, and I'm going to give it some directions. So this is north. East. South. And west in plan. Okay, so here's the question. You're coming along. Let's have a kid walking along with his or her mobile. And how are we going to identify that you are in the area so that we can bring up imagery that overlays on what we're looking at? So bear in mind, with this location-based AR, we can't do any clever, fancy image recognition to detect the statue, and in reality that's tricky. Depends on the lighting levels, depends on the direction you're approaching the statue from. We're simply doing it using GPS coordinates that are coming down from your phone and perhaps Google Maps. Okay, so here's the technique that works quite well. What we can do with GPS is we can detect that you're moving because, and let's just draw a little arrow here, this is a position you're in, and if we measure your GPS a few seconds later, you might have moved, say, to this position. What that means is that we know which direction you're going in. It's like little breadcrumbs that are taking us somewhere. So if we look at that in plan, then something very interesting is happening. I know through the breadcrumbs that somebody is walking in a particular direction. And I also know that with my GPS, which is accurate to about 3.5 meters, that I'm fairly close to the actual object of interest, the landmark. So I'm going to do a swoopy circle around here. I know that the user is somewhere in this circle, okay, within 3.5 meters. So by looking at the little breadcrumbs or the footprints, I also know that I've got into a particular direction. So I've known I've entered the circle and I know I'm going this way. So this actually tells you that the user is moving from west to east, entered the circle, is moving from west to east. So at this point you know that the user is basically facing the statue on this side. Okay, and at that point it means that you could do the overlay to interfere with what the user might be seeing. And that basically is all you need. Now, that's in some ways, with Ingress, it's slightly more sophisticated than you need with Pokemon Go, because these objects are more cleverly superimposed on landmark buildings than with Pokemon Go. Okay, so to recap, all you need to do is check that the user is moving. When they're moving, look at your GPS coordinates, so you know the direction. You know when they hit within 3.5 meters of somewhere. That tells you which way they're entering that circle, and then you can superimpose the image. And the fantastic thing about this is you don't need any of the fancy vision recognition software that means you need licenses and so on and so forth. So let's have a look at how exactly we can get the mapping function and the GPS into your website or your web app. So if you look at the demo examples, you'll see that there's a entry in here for maps. We just click on this, and when we open that up, there's 6 different demo files. So let's just go to the first one and have a look at that. Okay, so this one has actually opened up, well, it's a map of London, and it's showing several different Google Map views of London, so satellite views, road views, etc., etc. Let's just go and have a look at what the actual code looks like. Got this in brackets, open up, whoops. Cut and restart. Okay, so this is the maps code, and it's basically identifying 4 different Google Maps which are basically just divs with IDs set with the sizes. And then if we go down into the JavaScript, you'll see there's a function called myMaps, which is giving a bunch of options for each of the maps. So one of them is a road map, satellite, hybrid, and giving the latitude, longitude coordinates of where the map is and to what extent we want to zoom in. Pretty straightforward. And basically it's popping that into the ID. Okay, so let's have a look at another one. If we go back to our list of demos, go into Maps again. Maps 2 is doing something slightly different. This time it's now bringing up map of England and it's put a little marker on where London is, and I can use the standard Google controls to zoom in and out, all very straightforward. And it's at times like this that I really do actually think it's fantastic that we have Google at all, because it's worth having them around just so that we've got access to these fantastic mapping functions. Now let's go and look at what the code looks like, because it's pretty straightforward. We go in here, this is Maps 2 in the demos. Again, the div which has got an ID for the map with the size. And when we look at this, we've got the center of the map defined, and we're creating it with a center, with a zoom amount, and we're basically putting down a marker, so you can see that in here. Set down as being located at my center, okay, which is up here defined as latitude, longitude. Pretty straightforward. Let's look at another one. Just jump back. Look at Maps 3 this time. Ah, okay. So it's the same, but this time we've got a fun bouncy marker. So that's pretty handy. If we want to have a look at the code, what's going on? Well, not much difference, except we've got a little animation command here. Animation, Google Maps, animation bounce. Okay, the rest of it is pretty much the same. What else have we got? Let's look at the fourth example. Oh, and in this instance, what I've done is I've drawn a circle. Now, there's plenty of functions in Google, apart from being able to drop down markers. You can put down circles, polygons, lines between places, whatever you like pretty much. Lots of different basic shapes. And if you want to see the code for that, then here we are, creating the map again. This time we're showing Amsterdam. And if we look in here, we have created our circle. Google Maps circle. With a bit of information, it's transparent or translucent, and you're setting the colours, etc., etc. So all done by basic JavaScript. Now on to our fifth example. This time I've got a marker, and I've also got a little bit of text that is associated with the marker. So that's quite fun as well. Let's go back. Here's the code again, and you'll see here we got the little info window, which is putting in the Hello World content. So again, very straightforward. And now we can look at the final example, Map 6. This time we're actually bringing in a 3D image. I'm rotating it around here. So nice, I think it's a bit of Venice. And if we go and look at the code, you'll see I'm basically choosing what's called a hybrid map. Otherwise, pretty similar to the rest. I just have to give it the location. Okay, and that's really maps. If you want to go and look at all of the different commands that are available, there's examples on the Google sites, but also you can see quite a lot of this on the W3 Schools tutorials. So something you'll need to bear in mind when you are using the Maps API from Google is that if you're actually going to receive the coordinates, then you will have to get a key and a signature for authentication. Now, you didn't used to have to do this, but it's introduced relatively recently as a requirement. So some of my older examples don't have this, so they won't work anymore. But effectively, it's pretty straightforward. You get an API key, and once you've got that, then you can basically get map coordinates on the fly. And you can see this is the Google Maps API website. It's explained here. You won't need a paid plan for the sort of things that we're looking at as basic projects. So get your key, and then you should be able to get the code to work. The JavaScript API is the one to use, and there's plenty of examples in the Google website. So what about computer vision based AR? This technique uses the mobile device's processor to recognize image content that the camera is showing. There are a couple of ways that this can happen. First off is marker-based tracking using a specifically designed 2D marker. The marker is called a frame marker or a fiducial. The fiducial is typically a simple black and white pixel pattern. The marker is placed in the field of view of an imaging system which appears in the image produced for use as a point of reference or measure. A great example of this is the AR basketball app by Augmented Pixels, which is shown in the image. Users print out the marker, which is shown on the right, and the game superimposes a 3D basketball hoop for them to flick balls into. Markerless tracking using more natural content can be done in which an object is recognized. This could be a 2D image, or it could be a simple 3D shape, such as a cube or a cylinder. A natural feature tracking target, such as a road surface, can also be used, provided there is clearly visible planar texture that can be identified. Some systems can identify more complex objects, such as a toy car. As the object's complexity increases, so does the processing time needed to identify the object. For this reason, complex objects are sometimes identified using cloud services in which the intensive processing can be done on powerful remote servers. And you'll see from these two images two markerless AR examples. On the left there's one that's using a 2D image to superimpose the 3D, and on the right you're seeing a 3D Mario object that is being identified. And what about the humble QR code? Although QR codes are not the most advanced form of augmented reality, they are worth a mention since they are a great way to trigger location-based interaction, and users generally know what they are. A QR code is essentially a two-dimensional barcode matrix. QR means quick response, and it was invented in 1994 for the automotive industry to track vehicles. QR codes are great because the public generally knows what to do with them these days. The Shazam app recognises them, and Snapchat has Snap codes, and both have over 100 million users. The barrier to using QR codes is if people have to download a QR scanning app. The good news is that you could build the function into a web app for Android. With iOS web apps, it is a bit trickier as the user has to take a photo first, since Apple does not allow a web app much freedom with the camera. But let's think about two options. Firstly, how to create and use QR codes using third-party websites and apps. And secondly, how can you build QR code functionality into your own cross-platform web app? So first off, how to create and read QR codes using third-party websites and apps. The easiest way to use a QR code with a web app or app is to have it linked to a URL when the user captures an image of it with their camera. There are plenty of free websites that will create a QR code and let you do this. One example is Code Generator, which will also allow you to create other links. Here you can see the Code Generator website, and you'll see there's a number of options on this. One is to put in a URL, which will generate a code for us. So we could put in, I don't know, let's put in http://bbc.co.uk. We create the code, and there it is. You can download that, embed it, whatever you like. The other thing that a lot of people don't realise with QR codes is you can get them to create other responses, such as text. So I can write, "Hi, I am Tom." Create the code. There you go. If I put in lots of text, so let's just copy and paste that. Create another code. You'll see that the QR code itself is denser, it's got more pixels. That's because there's more information that it's got to communicate. And the thing to bear in mind is that as the pixels get denser, the likelihood of your phone making an error when it tries to recognize the pixels increases. So watch out for that particular issue. To read a QR code, the mobile user will need to run an app. I typically use QR Droid on my Android phone, which is free on the Google Play App Store. iOS actually has a QR reader built into the Passbook, and there are plenty of apps available as well. When I scanned my QR code, my scanning app opened the URL and had no problems. The sort of information that can actually be stored in a QR code includes URLs, texts, emails, even things like PDFs and images. Although, as I say, you've got to watch out for the density of the pixels. So you can build QR code functionality into your own cross-platform web apps. It's fine to have users detecting QR codes with a QR code reading app, but wouldn't it be better if you could actually build this into your web app itself? This helps overcome the user inertia that sets in whenever extra apps are needed. There's a simple site that both creates and reads QR codes, but does it for just URLs or text. And it works in Firefox, Chrome and Opera. So in my demo examples, you can see there's a folder there for QR code, and if you go into that, you'll see QR code index.html. So this is the JavaScript code that is on the website. It's been created by Lazar Laszlo, and it's got a few things it can do, like it can scan a QR code if you're on a device which has got the camera on, and you can also create a QR code. So at this point I could put in a QR code or text. So I could write hello. Oops. Hello there. Do create. And there we have a QR code. So this JavaScript is pretty straightforward to use in your own application. As I say, it's all contained there in the demos under QR codes. And what about 2D image recognition? Sometimes all you need is a 2D image recognition as opposed to full-blown AR. I've described several free options that can do this. each of increasing complexity and sophistication. Resemble.js, Pastec, and OpenCV are those three. Resemble.js is a free, simple image analysis and comparison program written in JavaScript that you can use. The images have to be the same size and aspect ratio for this type to work through, and there's no correlation for angled images. A more advanced way of recognizing images is to use Pastec. This is open source image recognition platform designed for mobile devices, which works with 2D images. It indexes and searches for images, and you can add pictures to your Pastec instance. Because you have to compile Pastec on your server, though, this option is not suitable for novice programmers. Once the application has been installed on your server, you can make calls to it. The code is available on GitHub, and Pastec is based on the free OpenCV libraries that are available for commercial purposes, so you can use it without paying a license. There's a free demo Android app in the Google Play Store called Display, and you can see that in the image. You can try this. The Display app tries to match up images that your camera takes with images in Wikipedia. The images don't have to be exactly aligned to match. It could also be at an angle. The image below is in Wikipedia, and you can use it to try out Display, either print out the image or take a photo from your screen. If you're an experienced programmer, then a set of free libraries called OpenCV are also worth considering for various image processing tasks, such as facial recognition and emotion recognition. Unfortunately, OpenCV is not available on HTML and JavaScript, so it requires you to build your native app or to run it from your server. There's also a number of commercial cloud-based image recognition services with APIs that have been springing up recently. So what about AR development tools? Well, the good news, as we covered already, sensor-based AR, you don't really need any special tools to develop cross-platform sensor-based AR applications. The 4 components you will need to use in HTML and JavaScript are access and display a live camera stream, and you could do this in Canvas. Identify the user's geolocation coordinates. Use the phone sensors to detect which way the camera is pointing. Superimpose any graphics or text onto the canvas video image. For computer vision based AR, the difficulty is it's remained a niche interest for mobile devices since it emerged 5 or 6 years ago. This means it hasn't become part of the HTML5 standards maintained by W3C. Thus far, there's no cross-platform solution for computer vision based AR. So unfortunately, it requires either a third-party middleware application or a custom coding approach that is based on the operating system that you're using. If you're familiar with the Unity game platform middleware, then you can actually use Qualcomm's Vuforia AR extension. If you haven't used Unity before, I'd advise you not to jump in and take this option until you've looked at alternatives, including possibly abandoning cross-platform solution in this rare instance. Some of the third-party AR applications that you could consider are Daiquiri 4D Studio, Aurasma, Meteo, Catchoom, Layer Creator, and Augment. What you can see in the image here is the Vuforia AR SDK. My open source principles are somewhat challenged because the computer vision based AR options are middleware and generally not open source. They're also platform specific, which I've been striving to avoid. So bearing in mind these reservations, if you want computer vision based AR, then I have to reluctantly recommend the Vuforia SDK for iOS and the Vuforia SDK for Android. One other choice you could make is to use the Vuforia plugin for the Unity middleware engine that I touched on. But in any event, we are at the cutting edge of technology, and we'll have to live with a platform-specific option. I believe this is better than choosing middleware, since it will at least allow you complete freedom to create your own app the way you want to and without licensing issues. What you can actually see in the image is a teapot that is appearing when that textured pattern, which is a printed piece of paper, is identified by the camera. So that's really the full gamut of AR, augmented reality, what we can do, we've covered QR codes, we've looked at full-blown image recognition through libraries and other services, and I guess things in between. So the location-based solutions which work so well with Pokemon Go. And I think that's what's worth remembering, is that although the 3D image recognition looks pretty fancy, Pokemon Go is the first AR application to really go crazy and reach mass audience, and it's using location based. It's just about the simplest technology and technique that is possible. So think very carefully before you plunge into the more advanced systems. They could be a lot of fun, but doesn't necessarily give you something that is compelling, that's going to be really popular. Thank you very much.